Good afternoon. I'm Hussain, former professor, Department of Chemistry, University of Dhaka. This is the 39th lecture of AS and A-level chemistry series. And this is on redox to electrochemistry. Let's go to the next slide. Yes, a redox reaction, which we discussed in a larger form. That is lecture 13 and lecture 14, where we defined oxidation reduction. We learned how to construct an equation of redox reaction for 11 half equations. We also used the concept of oxidation numbers to show whether a particular reactant is occurring. We discussed in details in AS level chemistry. This knowledge of AS level redox reaction, which we can say redox 1, in many books of A level, it is said redox 1 and redox 2. So redox 1, we had a long discussion about it, and now we are going to start redox 2, and which is electrochemistry. So before we go to electrochemistry, let's take a problem on redox reaction. What is the problem? It says that we have ferrous sulfate and we measured 1.3 gram of ferrous sulfate and dissolved in sulfuric acid, dilute sulfuric acid, and made it up to quantitatively at 100 milliliter. Here is a volumetric flask, and here is a burette, a pipette, and here is a burette. So burette, pipette, and measuring volumetric flask are quantitative instrumentation when we do experiment quantitatively. But mind it, the conical flask, here is conical flask, this is a conical flask. It is not used in quantitative measurement, but is being used in quantitative experiments. For example, we are putting this high sulfur solution in a conical flask, but this pipette where we took the sulfur solution, it is quantitatively measured. Similarly, if we take a burette, it is quantitative. If you take a solution in burette, it's quantitative, but when it drops out in the conical flask, though it is quantitative in the flask, it is, we didn't take quantitatively that amount. Okay, so here, the problem is that we take these solutions and made it sulfuric acid up to 100 milliliter. And then from this 100 milliliter, we took 10 milliliter of this solution, which required 12 milliliter of standard solution of potassium permanganate, 0.005 millar potassium permanganate. We are asked to find the percentage of iron in this gram of ferrous sulfate. That's what we are asked. So what is to do first? The first one is that we have to make a balanced redox equation for this ferrous iron 2 and manganate ion. So we have to have first find out the oxidation half reaction and also reduction half reaction, and find out the molar ratio of the reactants. So in permanganate, if this is the reaction of permanganate in acidic media, the manganese is 2 iron formed. So is it a reduction reaction, half reaction, or oxidation half reaction? What do you see? It is simply we look about the oxidation number of manganese ion in this here, and also in the half reaction, how it goes to. And you see that oxidation number here is +7 to goes to +2. That means oxidation number decreases, and therefore it is a reduction process. So this is a reduction half reaction. And for iron 2, if we go to iron 3, oxygen number increases, and therefore it is an oxidation reaction. And to cancel out the electron number, we have to multiply this half oxygen half reaction into 5, and therefore electron cancels out. So 5 moles of iron 2 is equivalent to 1 mole of permanganate iron. So we can find out the amount of permanganate iron we used, is it? So that is 12 milliliter. So you see in here the unit is in molar, so mole per dm3. So here we have to convert this 12 milliliter into liter, and that's what we have done here. And then we get this is the mole of permanganate iron. And now if we convert this mole of permanganate to mole of iron, we have to multiply it with 5, and therefore this is the mole of iron. Now, if we have to get it in gram, we have to multiply this into molecular weight of iron, and that's what we are doing here, and we get the gram here. So this is the mass of iron 2 we got from by experiment quantitatively, iron 2, and here the gram. So we can now find out the percentage of iron present in iron sulfide, 1.3 gram of iron sulfide, and the percentage is 12.8. So you can see how we are using this redox reaction to find out quantitatively the percentage of certain substance. Now we go to the next slide and see where we are applying this. We are applying redox reactions in electrolysis. What is electrolysis then? Electrolysis, we decompose a compound to its elements using direct current, and that is what we call electrolysis. Okay, then during electrolytics, what happened? The positive ion, that is cations, move to the cathode. When they reach to cathode, they gain electron from the cathode. These are two examples. Positive ion moving to cathode. When they reach to the cathode, they gain electrons and thereby forming this. For hydrogen also, gaining electron. So gain of electrons is reduction. We find it now. And reduction always occur in which part? That is at the cathode. Reduction always occurs at the cathode. Okay. What happens when we have negative ions? They move to the anode. And then when they reach to the anode, they lose electrons to the anode. Here you see, we gain electron from the cathode. Here we lose electron from the anode. And these are the example for this, what we have said. So loss of electron is oxidation, and oxidation always occurs at the anode. Okay, why do we have to have this electrolysis? Well, we can see that we can extract metals by electrolysis. That's a very important thing. There are metals whose ore could not be reduced with carbon. So we have to use electrolysis process to get. And we can also produce non-metals by electrolysis. We can purify some metals by electrolysis. So electrolysis is generally carried out in an electrolysis cell. Now we are showing an electrolysis cell here, you see. So that's that we have two electrodes. Here is the electrodes, these two electrodes, and then we have electrolyte. The compound, we say this is what is electrolyte in this beaker, and then we have positive electrode, which is anode, and a negative electrode, which is cathode, and we supply current for making electrolysis, and the current must be direct current. Must be direct current. And that is what all about electrolysis. Now we continue this. Now we have to use electrochemical cells based on redox reaction. A part of it we have said in the last slide, but the details we are showing here, how it happens. Let's like this. Okay, electrolysis cells are what we already said. It is based on redox reaction. This has got a practical and technological importance. For example, particularly fuel cells are now becoming an alternative to oil-based cell. Measurements of the voltage in cell helps us to see the feasibility and likelihood of redox reaction. So here we have shown this oxidation half reactions and reduction half reactions and overall balanced reaction of zinc and zinc solid, which oxidized to zinc aqueous solution, and then 2 electrons is released. So it is an oxidation half reaction, and this is a copper 2 ion which gain electrons, and this is a reduction half reaction. If we write down this and then make a valence solution, this 2 electron to electron cancels out, and we have this reaction. Zinc solid plus aqueous copper 2 ion, and then product is zinc 2 ion and copper solid. That's what we show here. Yeah. We take solution of zinc aqueous solution, 1 mole per dm, that is 1 molar solution, and then we have copper, 1 molar copper solution, and then we have a salt bridge to connect these 2 electrode, salt bridge. And then we have a high resistance voltmeter here to get the voltage we get from this cell. Okay. We said salt bridge. What is salt bridge there? There are, in the laboratory, there are a simple way that we soak filter paper of the saturated potassium nitrate solutions and keep this connect this to this beaker, to beakers. Okay, this is a simple salt bridge, but permanent salt bridge, generally it's a consist of porous solids such as sintered glass. So electrons tend to flow out from the zinc electrode that's from here, it flows out, and in the cathode through the external circuit. This is the external circuit, and the electromotive force, which is called EMF, shortening, the cell potential is about 1.10 volt under standard conditions. Please do remember that we are saying under standard conditions. We'll talk about it a little bit later, under standard conditions. Well, and this is what we are saying about comparing the voltage EMFs developed by their different electrochemical cells. The measurement should be under standard conditions, that's what we say. And then the standard conditions for electrochemical measurements as well as thermodynamical measurement, thermochemical measurements are same. The standard condition, what does it mean? That what is the temperature, how is the gas pressure, solution concentration? These are the standard conditions. So we took the standard condition, that is 298 degree Kelvin, that is 25 degrees Celsius, and gas pressure should be 100 kilopascal, and solution, the concentration should be 1 molar concentration. This is the standard conditions. And whenever we are writing electrochemical cell, or we are showing the voltage we got from electrochemical cells, we should have standard condition for this. when we refer anything, we will say that this is standard electrode potential. Here is the sign of standard electrode potential of the cell. This is a symbol we use everywhere for showing the standard electrode potential. One thing. Now, this is a what we call it. We are showing each half electrode and then the salt bridge and this cathode and anode. This is a shortened form called cell diagram. This is the cell diagram of zinc aqueous ion, and this is what the vertical one. Vertical one shows separate the different physical state of the half electrode. That this is the physical state. This is solid, but this is aqueous. This is the physical state. So it show the differentiation of by a solid vertical line, and that dotted line, which is called a salt bridge. And here is the representation of a cell diagram of a cell composed of zinc solid and zinc 2 aqueous ion and copper 2 aqueous ion and copper solid. This is how we represent a cell diagram of a little bit more explanation here that zinc oxidizes here, and this is the half reaction, and copper reduced, and that is the half reaction of the copper, and this is how reaction goes on, and that is the electrons by electrical circuit, the direction of change in electrochemical cell. Now we are talking about standard electrode potential. We have said this. The half electrode such as copper 2 aqueous and copper 7 makes the same contribution to the cell EMF of any cell so long as we measure it in standard condition. We will see that it should be standard condition when we are talking about EMF of a cell. So we go to show you how we make a standard electrochemical cell. So that is what is we have a reference electrode. We have to use a reference electrode against which we compare the other electrode system. So reference electrode means standard hydrogen electrode, and by convention, standard hydrogen electron, the potential is EMF is 0. So here it is a standard hydrogen electrode symbol. Here is standard hydrogen electrode symbol. And this is what we, in big details, you can show that we have hydrogen gas at 298 Kelvin and 100 kilopascal pressure. Here it is. Yes, it is. And then with the acid solution here, and that should be 1 molar, a concentration should be 1 molar. And platinum electrode, here it is platinum electrode coated with finely divided platinum there. This is platinum electrode, and there we have some porous film. So hydrogen gas will evolve that can escape through this first. And this is copper sulfur solutions. Copper sulfur solution, and we have copper strip here. So this is a half electrode. So if we compare this becomes then the cell diagram of this one cell diagram, and the cell EMF of the cell is plus 0.34. More simple representation is like this, that oxidized form here and reduced form here is here, and cell EMF is 0.34. This is what it is. We take this slide now and also show if we have redox potential in about standard electrode potential, I said setting up a hydrogen electrode is rather difficult and also a bit costly, and it has to be maintained properly. Therefore, we can use standard electrode potential for a silver chloride electrode or calomel electrode as a reference electrode, and that is, these electrodes are commercially available and that can be calibrated. They are already calibrated against the standard hydrogen electrode. So calomel is mercury 1 chloride. The cell reaction and electrode potential related to hydrogen electrode. For a calomel electrode is like this. This is what it is. So cell of this, the EMF is plus 0.27. So we use this as a reference if we do not have standard hydrogen electrode in the laboratory. So this can be used also. And then if the reaction here, you see, this is the reaction going forward, and we get the EMF of the cell is like this, 0.27. But if we now have this mercury 1 in a liquid and then chloride 1 and get this solution, so this is, then we reverse it. The opposite sign is for the EMF of the solutions. That we have to also remember. And then this is what we showed as a cell diagram of this. The particular thing here is that we have ferric iron in aqueous solution and ferrous iron. So both are in aqueous solution. Therefore, we have to use a shiny platinum inert electrode to complete this cell. So this is what it is, the hydrogen gas and then hydrogen ion, and then the salt bridge and ferric ion and ferrous ion, and that makes a cell diagram of about this picture what I showed here. With this next one, what we are talking, using of E naught, that is the EMF, how to predict if the reaction occurs or not. We can we can explain this very well, that these are the half reaction of cells, and that is the standard electrode potential of the cells, half cells. And what we can see here, that the standard electrode potential is going down and getting negative and negative and negative. So this is a more strong reducing agent, this one. And then with negative, less negative number and then positive number in this way, the positive is the weakest reducing agent. Same goes here, strongest oxidizing agent for this one. And if we go down, then it becomes weakest oxidizing agent. So from here and the electrode potential, we can also say which reaction is feasible and which reaction is not feasible. That's what we will take in the next lecture, and hopefully next lecture we can finish the redox 2 syllabus of A-level chemistry. Thank you for your patience, and we look forward to see the next lecture, that is the 40th lecture of A-level chemistry. Thank you very much.